Thank you so much for the nice invitation to speak at what looks like it's going to be a really interesting conference. So today I'm going to speak about joint work with Daniel Greer, Luke Schaefer, and my student Alex Kersner, all of whom are at the University of Waterloo. And the topic is fast simulation of planar Clifford circuits, and we have a paper on the archive. So this is kind of the structure of the talk. First, I'm going to tell you some introduction and motivation for why we studied what we studied. Then I'll talk about what our results are, and then at the end, I'll discuss our techniques. So, we believe that quantum computers can't be efficiently simulated by classical computers. And so then you might ask, why should we study classical simulation of quantum computers? Because if we expect that classical simulation algorithms have to be slow, then why should we improve them? And there's at least three reasons, which I like to list at the beginning of a talk like this. One of them is to understand what exactly is classically hard about simulating quantum computers, to understand where the boundary lies between classically simulable and quantum advantage. We can use classical simulation algorithms to verify and validate small quantum computers. And of course, we want to probe this belief and really push it from many different directions to give some confidence that it's really true. Now, if you ask about, what are the algorithms for classical simulation of quantum computers, the answer for the most part is fairly simple. I mean, most algorithms that we know of, at least in a general setting, have exponential scaling in the number of qubits or the number of gates. And so, for example, the most naive algorithm, we would just store an n-qubit state as a complex vector of length 2 to the n, and we would update that vector by sparse matrix multiplication every time we apply a gate. And that sort of very naive algorithm requires, an amount of memory which is exponential in n to store the full state vector, and also a runtime which is, proportional to that memory cost. Another type of algorithm would be what's sometimes called the Feynman algorithm, where we expand an amplitude of a quantum circuit as a matrix product or sum over paths. And now computing each term in this sum, which expresses the matrix product, each term can be computed using a small amount of space, but there's a very large number of terms. And so here the memory requirements are now only polynomial in the number of qubits and the number of gates, but the runtime is again exponential in the number of gates. And of course, for a reasonable circuit, the number of gates will be greater than or equal to the number of qubits. So both of the algorithms I just described to you should be viewed as exponential in the number of qubits at least. On the other hand, if you relax the idea of looking at the most general types of polynomial-sized quantum circuits and instead try to exploit some kind of special features of the circuits you might be interested in, such as circuit geometry, then we know that you can do that. So, for example, if we take a quantum circuit and construct a graph in the following way. So first we add a vertex, here drawn in black, for every gate in the circuit and every wire. So I've just put a vertex on every gate and every wire. And then we add edges that describe, which wires are connected to which gates, and so on. Then we get a graph. And it was shown by Markov and Shi in 2005 that a quantum circuit can be simulated with runtime which is not necessarily exponential in the number of qubits, but rather scales exponentially in the tree width of this graph. And that tree width can be less than, for example, the number of qubits. And we'll see some examples of that. The tree width, I don't expect you to be familiar with this quantity. Later in the talk, I will define it, but for now, you can think of it as some kind of measure of how tree-like the graph is. So a tree has tree width 1. A planar graph has tree width, which is square root the number of vertices, and the tree width is always at most the number of vertices. So what is the idea of Markov and Shi simulation? It's Well, roughly, to view the circuit as a tensor network and choose an ordering to contract all the edges of the tensor network in order to minimize the memory and the runtime. So let me, instead of defining tree width and being completely precise about this, let me just give you some examples. If you have a circuit where you have nearest neighbor gates in one dimension, so all gates act between nearest neighbor qubits. So here on the horizontal axis, we have n qubits, and on the vertical axis, and on the horizontal axis, we have a depth d, which I want you to think of as being like a constant, like 5. So this is a 1D circuit. If we do this procedure of mapping it to a graph, then we get a grid graph where you have n vertices on the vertical and roughly twice d vertices in the horizontal. And the tree width of that graph is linear in d. So the simulation runtime in this case is, if d is a constant, this would be a polynomial time simulation. And that corresponds to the well-known fact that one-dimensional constant depth circuits can be simulated using matrix product state techniques. It's really the same thing. If you take, for example, a 2D circuit, where now the gates act between nearest neighbors in 2 dimensions, you have n qubits and again some constant depth d. I didn't dare to draw that thing. When you map it to a graph, you'll get a 3D grid graph, and now your simulation runtime will be exponential in d square root of n. So even though this is, kind of a poor scaling with n, it's much better than exponential in n, which is what a naive algorithm would get you. And, the fact that you can exploit circuit geometry in the simulation of quantum circuits is not only of theoretical interest. In practice, this fact has been used in implementations like the ones from this table, which is from a paper of the Alibaba group from 2018. You can see that there are several simulations here, many of which use these sort of tensor network contraction techniques along the lines of Markov and Xi. Okay, so the whole point of all of that was just to tell you that we know that to simulate a general quantum circuit seems to require resources exponential in the number of qubits. But if you restrict your attention to circuits with nice geometries, then sometimes that runtime can be improved. And in this talk, we're going to exploit circuit geometry in the simulation of a very special family of circuits called Clifford circuits. So what is a Clifford circuit? Many of you may have seen this before, but I'm going to describe it a little bit on this slide. A Clifford circuit is composed of gates from the set Hadamard, single qubit phase gate, and controlled Z gates. And it's been known for a long time, the Gottesman-Knell theorem, which appeared in Gottesman's 1997 work and is attributed to Gottesman and Manning-Mill, showed that quantum circuits that are composed only of Clifford gates can be simulated in polynomial time on a classical computer. So this is a very different ballgame from the types of simulation I was talking about just a moment ago, where we were talking about general circuits requiring exponential time and nice geometries, improving that to some kind of sub-exponential or mildly exponential runtime. And I've listed here some important works in the development of Clifford simulation techniques, because on the next few slides, I want to describe to you some of the features of Clifford circuits and the states that they prepare. So the state that is prepared by an n-qubit Clifford circuit acting on, say, a basis state is a stabilizer state. And a stabilizer state can always be written in the following form. It's parametrized by an affine subspace of binary strings, a quadratic function, and a linear function, linear Boolean function. And I like to think of a stabilizer state as some kind of generalization of a quadratic function. You may or may not find that to be helpful. More importantly, this state, to store it, you just need to store the description of this affine subspace, quadratic function, and linear function. And it's fairly clear that just from what I've written on this slide, that you can do that using only order n squared bits, unlike a general quantum state on n qubits, which would require a 2 to the n memory cost to store. It's also true that you can update this representation efficiently under the action of Clifford gates or measurements. I want to say just briefly that this presentation in terms of an affine subspace quadratic function and linear function, which I think originally appeared in the work of Dehaene and Demour and Van den Nest, this is sort of not the original way that stabilizer states have been presented. And of course, most of us know that there is another characterization in terms of the stabilizer group, which is generated by a set of commuting n-qubit Pauli operators and has the property that each one of those Pauli operators acts on the state and gives you back the state. So the stabilizer state is a +1 eigenvector of every element of its stabilizer group. And again, as you may know, the generators of a stabilizer group can be recorded in a binary matrix with order n squared bits in it, and they can be manipulated using linear algebra. Okay, so all of that is to say that we know how to store a stabilizer state using n squared bits, and we know how to update it efficiently, but I would like to be a little bit more precise about the cost of updating the representation of a stabilizer state under the action of measurements or gates. So if you want to apply a single or 2 qubit Clifford gate to an n qubit stabilizer state, you can do that in time linear in n. And it's also true that if you want to measure a qubit of an n qubit stabilizer state, you can do that in time order n squared. And that order n squared is that is the best known algorithm due to Gottesman and Aronson from 2004. For our purposes, later in this talk, it will be interesting to look at the case where we're measuring all of the qubits of an n qubit state. And in that case, if you just take Gottesman and Aronson and measure each qubit sequentially, you would get a runtime of order n cubed. So, or in other words, if you wanted to measure k qubits, it would be k times n squared. And one of the contributions of our work is that we improve that sort of batch measurement task to have a runtime which is up to log factors k to the omega minus 2 n squared, where omega is a number between 2 and 2.37 roughly. That is the exponent for matrix multiplication. So for example, if you want to measure all of the qubits of an n qubit state, this would tell you that you can do it in time n to the omega, which is the same runtime as multiplying two n by n matrices, which you might not be surprised by, but didn't appear to be known or written down in the literature before our work. Another thing you can do is if you want to apply any number of controlled Z gates on any subset of qubits, you can do that in time n to the omega as well. And one of the reasons for putting this up here on this slide, and the only thing you need to remember about updating stabilizer states, is that for the purposes of this talk, any operation that you want to perform on an n qubit stabilizer state, anything that I'm going to do on an n qubit stabilizer state, can be done in time n to the omega. So measure all the qubits, apply controlled Z gates on any subset of qubits. Anything like that, it takes time at most n to the omega. And that's going to be something that I'll refer to later on. Okay. So although Clifford circuits can be simulated in polynomial time, we do know that they can provide a speed up over classical computers in a certain sense that I'll describe now. In particular, in joint work with Sergei Bravi and Robert Koenig from 2018, we showed that even if you have a Clifford circuit of some constant depth, and even if that circuit has a nice geometry, like a two-dimensional geometry, that type of circuit can solve a linear algebra problem that requires logarithmically increasing depth to solve using a classical computer. So what is this linear algebra problem? Let me just describe it to you in a couple of slides. We start with a symmetric n by n binary matrix A, and let us define the kernel of A, which is the set of binary strings that are annihilated by A mod 2. And it's going to be, we're going to have to define the following quadratic form Q of x, which is x transpose AX mod 4. Here x is a vector of n bits. So all of these things are defined only in terms of this matrix A, which is the input to the problem. And it's not hard to show, actually, let me, so it's not hard to show that if you restrict your attention to binary strings in the kernel of A, then this quadratic function, this Q of x, it drops down to a linear function. So, there's something funny going on here with the mod 2 and the mod 4, because if everything was mod 2, and if you looked at this quadratic function on the kernel of A, so what I was saying is that if this quadratic function was defined as x transpose AX mod 2, and if we looked at it in the kernel of A, then it would just drop from being quadratic to being a constant function, the function 0. But because we have this mod 2 and mod 4, something slightly funnier goes on, which is that when we look at the quadratic function in the kernel of A, instead of dropping down from quadratic to constant, it drops down from quadratic to linear. So in other words, if we look in the kernel of A, the quadratic function is parametrized by a bit string z that tells you what linear function it is, which is the fact that's written here. And this is not hard to show. And the linear algebra problem that we consider, we call it the hidden linear function problem, where you're given this matrix A, and your goal is to find that parameterization of the linear function that's hidden inside of the quadratic function that you're given. Now, there is an efficient classical algorithm for this problem. This is a linear algebra problem, and I want to tell you what that algorithm is, because it's very simple. First, you find a basis of the kernel of A using Gaussian elimination. So you find this basis x1, x2 up to xk. Then, for every basis vector, you plug it in to this formula, Q of x equals 2z transpose x. And each one of those equations is an equation for z. So now you get a system of linear equations for z, so then you do linear algebra again and solve for z. So you have to do 2 linear algebra tasks in sequence to use this algorithm. But it will run in polynomial time on a classical computer. Now, so this hidden linear function problem, it can be solved in polynomial time on a classical computer. It turns out, for our purposes, we want to solve it in constant depth on a quantum computer. And to do that, we actually restrict our attention to a subset of instances which have a certain two-dimensional structure, which we call the 2D hidden linear function problem. And that subset of instances just corresponds to the case where if we view A, the symmetric binary matrix, as the adjacency matrix of a graph, then we only want to consider inputs or matrices A where it describes a subgraph of a root n by root n grid. Okay, so that's the linear algebra problem. And as I said, there is a constant depth circuit that solves this problem. I'm not going to really describe what the circuit is, although I guess I did include this picture, which may or may not help you. But the point is that it can be solved with certainty using a constant depth quantum circuit. And not only that, the circuit, well, as I just said, is constant depth. It's shallow, and it's two-dimensional. It's a Clifford circuit in a 2D geometry. So all gates are Clifford and act between nearest neighbor qubits in 2 dimensions. On the other hand, we showed in our paper that this hidden linear function problem, even though it can be solved in polynomial time on a classical computer, it cannot be solved in constant depth on a classical computer if you use gates with a constant number of inputs. Now, this result was then strengthened by Bene, Watts, Kothari, Schaefer, and Tull, who showed that for this problem, even a more powerful class of constant depth classical circuits still can't solve the problem. And that more powerful class allows the circuit to use unbounded fan-in and OR gates. In subsequent work, we showed that there is a version of this type of separation that works even if your constant depth quantum circuit is affected by noise. And then Greer and Schaefer later showed that you can make this task even harder for classical circuits by asking for the solution in a two-round interactive way, where you ask for part of the solution in the first round and then ask for the second part of the solution in a second round of questioning. Okay, so all of that is to say that, we know that Clifford circuits, even though they can be simulated in polynomial time on a classical computer, there is a quantum advantage as measured by the depth of the computation. And part of the motivation for our work is to understand whether or not there's also an advantage in terms of the total runtime, meaning the total number of gates or steps required to solve the problem. And why would you think that might be the case? Well, the quantum algorithm, which solves this 2D hidden linear function problem, it's constant depth on n qubits, and so it necessarily has a linear number of gates. On the other hand, the classical algorithm that I just showed you uses n to the omega gates, where omega is a number that's greater than or equal to 2. And so then the question really is, can that classical algorithm be improved, or is this a quantum speedup, n versus n to the omega? Now, one reason to think that maybe you could improve the classical algorithm is that we know that there are fast versions of linear algebra for other linear algebra tasks on planar graphs. In particular, George in 1973 introduced something called nested dissection for solving linear equations with a kind of 2D structure, and that has been generalized by Lipton, Rose, and Tarjan to planar graphs, and then further generalized by Alon and Yuster to the version that I'm going to tell you about on the slide. And what they showed is that if you have the adjacency matrix of a planar graph A, and you try to solve a system of linear equations AX equals B, let's say that everything is over the binary field, and if you assume that A is non-singular, then there is an algorithm which solves this system with runtime order n to the omega over 2. So there's a square root speed up over the standard n to the omega linear algebra runtime. And this algorithm uses a kind of divide and conquer approach, which George called nested dissection. But so you might think that, because this 2D hidden linear function problem has a kind of two-dimensional structure, you should be able to use this kind of fast linear algebra on planar graphs to solve it with a square root speedup. But unfortunately, this fast algorithm does not seem to directly help that classical algorithm. And the reason is, so here I've repeated the classical algorithm for the hidden linear function problem. So remember, we have a matrix A, which describes the adjacency matrix of a planar graph. That's good because we want to use planarity in our algorithm. So in the first step here, when we solve for a basis of the kernel of A, we do have a matrix A with planar, which is planar. So we might hope to do this first step in time n to the omega over 2. But then in the second step, when we have to do linear algebra again, using the solution x1 to xk of the first step, now we've lost our planarity. So it's really not clear how you can exploit planarity in this algorithm as a whole. But in our work, we do show that kind of like the moral or the strategy that's used, this kind of nested dissection or divide and conquer method, can still be adapted to this Clifford simulation task. And so now let me segue into a description of what it is that we actually show in our work. So we consider Clifford circuits where all of the 2-qubit gates act on the edges of a planar graph. So for example, you might have a qubit at each vertex of this graph, and then you might apply some single qubit Cliffords, and then you might apply some controlled z's to nearest neighbor qubits, and then more single qubit Cliffords, and then you might measure. So that's an example of a Clifford circuit with nearest neighbor gates on the edges of a planar graph. We're going to be interested in the output probability distribution, which is just, you apply this Clifford circuit with a planar geometry and then measure in the computational basis. And what we show is that if you have a depth d Clifford circuit of this type on a planar graph, then there is a classical algorithm that samples from the output distribution with a runtime n to the omega over 2 d to the omega. This O tilde means that we're hiding log factors. So for example, if d is a constant, if you have a constant depth Clifford circuit on a planar graph, this is an n to the omega over 2 runtime, which is a square root speed up over, the n to the omega, which you would get from using fast linear algebra. I should mention that the best previous algorithm was n cubed, because even the n to the omega improvement comes from our work. Another point to note is that if this exponent omega, we don't know what its value is, and we know that it's greater than or equal to 2 and less than or equal to roughly 2.37, but it's possible that it is equal to 2, and if that turns out to be the case, then this would be a linear algorithm, which would match that would then match the runtime of, for example, the quantum algorithm for the 2D hidden linear function problem, if that were the case. So this theorem is actually not the most natural way to phrase our results. It's a consequence of our main technical result, which is phrased in terms of quantum graph states. So recall that for any n vertex graph, we can define a graph state on n qubits, where we take the all zeros state, apply Hadamard's to all qubits, and then apply a controlled C-gate to every edge of the graph. We want to consider a problem or a situation where we're given a Pauli basis, so an x, a y, or a z for each of the n qubits. And then we take the graph state, and then we measure each qubit in the given Pauli basis. So here I've written this formula where u bases is supposed to be just the single qubit basis change for every qubit that maps, the x basis to the z basis or the y basis to the z basis and so on. So of course, this is a very special case of Clifford circuit simulation, because we're only considering Clifford circuits where you prepare a graph state and measure each qubit in a Pauli basis. And so just formally, we define this graph state simulation problem where you're given the graph, you're given a Pauli for each vertex, and you want to output a binary string sampled from the distribution you would get from doing this measurement. And it should be noted that this problem turns out to be equivalent to the hidden linear function problem. And if you consider this problem on a 2D grid graph, then this is the problem that achieves a quantum advantage in terms of circuit depth. And moreover, if you care about the more general Clifford circuit simulation task, that can be reduced to this problem using well-known techniques from measurement-based quantum computing. And that kind of reduction is how we get the other version of our theorem that I mentioned just a moment ago. But the main theorem that we prove is that if you want to solve this graph state simulation problem, you can do it for any planar graph with runtime n to the omega over 2. So again, you get this square root speed up over the n to the omega algorithm by exploiting planarity. And now I'm going to tell you about how we prove this main theorem. So I'm happy to just stop if there are any questions at this point and address those. Okay, if not, then we can continue. But feel free to jump in if you do find that you have a question. So in terms of techniques, I would like to first illustrate this algorithm in the special case of a 2D grid, where things turn out to be quite a bit simpler than the more general case of planar graphs. If you have a 2D grid with n qubits, let's say it's a root n by root n grid, and remember our goal is to prepare this graph state and measure each qubit in a given Pauli basis. But we want to simulate this on a classical computer. So let's just go over what is the most naive way you could do this. Well, first you would start by storing the stabilizer state, which is just all zeros. And we're going to use a representation of stabilizer states that requires n squared qubits even to store this one. Sorry, n squared bits. So here I've drawn in red each qubit because this is kind of a shorthand for red means those are the qubits that we're currently simulating in our classical simulator. So we're storing the state of these n qubits as a stabilizer state, which requires n squared classical bits. Then we apply the controlled z-gates on all of the edges. Remember that since we have n qubits here, this can be done in time order n squared. And then, oh, sorry, excuse me, let me explain that better. So the number of CZ gates is n, and each gate takes a linear, like order n time to apply. So the time required to apply n CZ gates is order n squared. And then we measure all the qubits. And as I mentioned before, we can measure all the qubits of an n qubit state in time n to the omega. So when I measure the qubits, they're not stored in memory anymore, and my shorthand for that is that they turn blue. And that's going to be, helpful later on when we describe more complicated algorithms. So this algorithm is very simple. We just start with the stabilizer state all zeros. We apply each controlled z-gate, and then we measure all the qubits. And the total runtime is asymptotically n to the omega. So that's our kind of baseline. So let me now show you how you can improve upon that algorithm. This is what we call the sweeping classical simulation. This algorithm was actually presented in our 2018 paper with Bravi and Koenig. In this, we would start by just initializing the qubits in the leftmost two columns in our classical memory. The number of qubits there is order root n. So the storage cost is root n squared, which is order n. Then we would apply the controlled z-gates that are only within those leftmost two columns. Remember that I said that we can apply any number of controlled z-gates in time number of qubits to the omega. Here the number of qubits is just root n, because we're only storing these ones in red. So the time to apply just those controlled z-gates is n to the omega over 2. Then we measure the qubits in the leftmost columns. Those are gone from our classical simulator. That can be done again in time n to the omega over 2. And then we continue. We apply the controlled z-gates in the next column, measure, apply z-gates, measure, and we move from left to right, sweeping in this way. And we are only ever storing a state of order root n qubits at any given time, because the blue qubits are out of our memory and the black qubits haven't been initialized yet. And so the total cost of this, we have to sweep from left to right. So there's root n sort of steps, and each step takes time n to the omega over 2. So the total runtime here is n to the omega plus 1, all divided by 2. Now, you could compare this to the naive algorithm. Let's say omega was 3, because in practice, if you implement this, omega will be 3. The naive algorithm would be n cubed. This algorithm would be n squared, so it's clearly better. But it turns out that this sweeping algorithm is not the best you can do. And the better algorithm that achieves the n to the omega over 2 runtime is a recursive one, which works in the following way. First, we recursively simulate 4 subgrids, each of size roughly n over 4. And so the cost of that is 4 times the cost of simulating a grid of size n over 4, whatever that is. So let's call it the function t of n over 4. But when you simulate those 4 subgrids, the ones that I've drawn here, you want to leave the perimeter vertices unmeasured, those red vertices. So you simulate them, you measure all the qubits inside, but you leave the perimeter vertices unmeasured. And the reason you're going to do that is because now you need to connect them all up by initializing these kind of window frame qubits in between and performing the remaining controlled z-gates. The number of qubits that are left now to initialize is order root n. So this takes time n to the omega over 2. And then you measure the remaining qubits. And you can either leave the perimeter unmeasured if you're recursing, or you can just measure everybody if you're at the final step. And the cost of that is, again, n to the omega over 2, because you have, at this stage, when you're measuring the remaining qubits, you have only root n qubits being stored in the memory. So we get a recursion for the runtime, which says that the runtime of simulating n qubits is 4 times the cost of simulating n over 4 plus this n to the omega over 2 term. And if you solve this recursion, you get that the n over to the omega over 2 term dominates, and the total runtime is in fact asymptotically up to log factors n to the omega over 2. And so this, in the kind of practical regime where omega is 3, this improves upon this naive algorithm, which has a runtime of n cubed, as well as the sweeping algorithm, which has a runtime of n squared. And so this would have n to the 3 over 2 runtime. And this is similar to this nested dissection technique of George for solving linear equations on a 2D grid, but it seems to also have some important differences. Okay. So my co-authors implemented these algorithms without using fast matrix multiplication. So in fact, for their algorithm, omega should be set to 3. And you can see that in practice, the naive algorithm is very bad compared to both the sweep and the recursive algorithm is in fact the best. And here you can see that this plot goes up to roughly 4 million qubits, but my co-authors were able to simulate a system using the recursive method of 400 million qubits, which is really quite remarkable. And the lessons here, which I would like you to take away, and maybe we can, we're going to soon move on to the more general case of planar graphs. The lessons that we learned from this is that this divide and conquer is an important strategy. And, when you're simulating these Clifford circuits, it's important to only store the qubits that you need at a given time. And this idea of scheduling the measurements in such a way that you minimize the number stored at any given time is very important. But unfortunately, scheduling what we did here involved just scheduling the gates and the measurements. But we don't know actually how to handle more general planar graphs using only those ingredients. And in fact, there's an important difference between our algorithm on more general planar graphs and this algorithm that I just showed you for the 2D grid, which is that we will need to have some duplication of qubits. And you'll see how that goes. But really the technical tool that allows us to sort of do this, to generalize this is the notion of tree decompositions that I mentioned earlier in the talk, and which was also key to this Markov and Xi tensor network simulation method for general circuits. So let me now tell you what a tree decomposition is briefly. So here is an example from Wikipedia of a graph and a tree decomposition of that graph. So a tree decomposition is a tree along with a bag for each node of the tree. So the bag is a subset of vertices, which is assigned to each node or vertex of the tree. And the bags have to satisfy 3 properties. Firstly, every vertex of the graph G has to be in a bag. Secondly, for every edge of the graph, there should be a bag that contains both endpoints. So for example, here, if we look at the edge BG, then indeed we find a bag of the tree decomposition that contains both B and G. And in fact, on this example, there's two such vertices. Thirdly, if you look at the bags that contain any given vertex, like for example, this vertex B, they should be connected in the tree. And so here you can see that they are indeed connected. So those are the 3 properties of a tree decomposition of a graph. Now, the important quantity that we're interested in is the width of a tree decomposition, which is the maximum number of elements of a bag minus 1. So in this example, each of the bags has size 3. So this is a width 2 tree decomposition. The minus 1 is just sort of a convention so that a tree has tree width 1. So the tree width of a graph is, the minimum width of any such tree decomposition. And as I said, trees have tree width 1, so you can always find a tree decomposition where the bags have size 2. And the other remarkable fact, and the thing that's relevant for us, is that planar graphs always have if you have an n vertex planar graph, it will always admit a tree decomposition of width roughly square root n. And moreover, that such a 3D composition can be computed in linear time, in time order n, using this notion of using the planar separator theorem. And this algorithm that computes this 3D composition for you, it really does have a kind of divide and conquer, well, it can be viewed as a divide and conquer method. I guess that's all I'll say about that. Okay, and the 3D composition that you get from this Lipton-Tarjan paper, which has width root n, can be massaged into what we call a nice 3D composition, which I've drawn an example. If we take this graph, where we just saw this width 2 3D composition, here is an example of a nice 3D composition of the same graph. The nice 3D composition has a few properties that we are going to use. Firstly, the tree is rooted, so there's this root vertex at the far right. Secondly, there's 3 types of nodes, here coded as green, pink, and purple. The green nodes are nodes where vertices are introduced, so they have no children. Or sorry, excuse me. They either have no children, in which case all of the elements of the bag are new, or, for example, this bag here, BFG, this introduces the vertex F from its child, which only has BG. There's also forget nodes, which, like this node BC, here we've forgotten the vertex A. So if you look at it has one child, and going from child to parent, you lose a vertex, or possibly more than one vertex. The merge nodes, these purple nodes, they have 2 children, and the bag of the merge node is the union of the 2 bags of the children. The nice 3D composition of a planar graph, again, will have width root n, order root n, and it also has the feature which comes from this kind of divide and conquer way that it's constructed, which is that the bags get smaller in a geometrical fashion from the root to the leaves. And the thing that we will use, that is kind of the quantitative version of the statement, is that if you take the sort of, sum of the bag sizes to some power c, which is, then this is upper bounded by, n to the c over 2. So you can think of the largest bag, which has size roughly root n, dominates. Okay, so that's a nice 3D composition of a planar graph, and we can compute these in linear time. So now I have to tell you, how do we use this nice 3D composition to simulate the Clifford circuit? So you start with the graph, you construct the nice 3D composition, and then we have a kind of method to replace every bag of the 3D composition with a little gadget. And so we can map this 3D composition to a Clifford circuit in a certain way that I'm not going to fully describe here, but here is an example. For the introduce, when vertices are introduced, like for example in this introduce node, we add a qubit. So here you can see that, like, because the 3D composition, it has, for example, C, the vertex C is in this bag, but it's also in this bag down here. So here on the left, we have a qubit for vertex C here, but we have another one for vertex C here. So that, you can see that in the circuit, there's a duplication of qubits in the original graph that we cared about. When you forget vertices, like at these forget nodes, then the sort of, what you do here in this circuit is you apply the CZ gates that act between that qubit and other qubits. So you do them at the very last moment. In the merge nodes, there's this little gadget that you're supposed to do. So you take one copy and the other copy, and you do a C0 gate and then measure one of them. We call that measurement a merge ancilla measurement. And this circuit that we construct from the 3D composition, it has a couple of properties. So first of all, when you make these merge ancilla measurements, if you get the measurement outcome 0, then the gadget implements the following isometry. And I don't expect, I have not fully explained this, but it follows from that and from the structure of graph states that if you get the measurement outcome 0 for all of the measurements that are in these purple gadgets, then the state of the remaining qubits, these qubits that are at the output, is in fact the graph state. You see that the qubits here, like A, E, and these pink ones, the ones that are all left over once you've made these purple measurements, there's one qubit now for every vertex in the graph. And so if you get the right measurement outcomes for each of those gadgets, then the state will be the graph state. So this circuit is just, you can think of it as a way to prepare the graph state if you get the right outcomes for all these purple measurements. So why is that useful? Well, it turns out that the simulation of this circuit can be done in a way that is faster than the naive simulation, and it gives you this. Okay, so let me explain. So if you classically simulate this circuit left to right, and then measure all the qubits in the given Pauli bases, because we're trying to simulate this Pauli measurements on graph states, then the cost of classically simulating this circuit is just the sum of the bag sizes to the omega. And the reason for that is that, remember that I told you that if I just look at this part of the circuit, like just these two bags, then I told you that the cost of any operations on like m qubits, any Clifford operations, is order m to the omega. And so this circuit has the property that if I'm going from left to right, first I can simulate this part, and I can apply the gates on this part separately. When I merge them, I have to consider, the full system consisting of the two children. And so somehow the largest system I ever have to consider at any given time consists of a bag and its children. And I can upper bound the cost of classically simulating the circuit from left to right as the sum of the bag sizes to the omega. And I mentioned earlier that the nice tree decomposition has the feature that the bags get geometrically smaller from the root to the leaves. And so when you have a sum like this of the bag sizes to the omega, you can upper bound it as order n to the omega over 2, because the largest bag size dominates, which has size root n, because it's a tree width and decomposition. Now, I mentioned that this circuit only does what we want if we measure all the purple qubits in the 0 state. So if we get lucky, then we're done, and we've classically simulated the graph state measurements in time n to the omega over 2. But it turns out that if you don't get the right outcomes, then there is a linear time algorithm to map incorrect measurement string that you simulate to a correct one. And that step is just the same as finding a stabilizer of the output state that maps that output bit string to one where all the purple measurement bits are 0. And it's not hard to show that you can do this in linear time. Okay. So that is our algorithm. And in our paper, we give a few extensions and generalizations. Firstly, we consider, our algorithm, what is the property of planar graphs that it exploits? Well, the property is that, for such graphs, you can get a low tree width tree decomposition in linear time. But if you give me a tree decomposition of some other graph, and it has some width t, then you can run our algorithm and you will get a classical simulation in time n times t to the omega minus 1. The challenge here is that, in general, it may be hard to compute a good or low tree width decomposition of a graph, even if one exists. Planar graphs are very special because, you can compute these low tree width decompositions in linear time. And I would say the second part is maybe the most important extension, which is that we consider a more general problem, really, where you consider graph seed simulation, but you're allowed to post-select some of the measurement outcomes, and then sample from the conditional distribution after that post-selection. And for this step, we develop the correction step that I mentioned just a moment ago, and I said you can find this linear time algorithm. that correction step turns out to be more involved for this post-selective graph state simulation. But it turns out that the correction step is actually equivalent to solving a system of binary linear equations on a planar graph. And we realized this afterwards, and it turns out that like our algorithm for doing this correction step, it actually furnishes a new fast algorithm for this problem of solving binary linear equations on a planar graph. And not only that, but our algorithm, it works in a slightly more general setting than the previous best method due to Alon and Yester, because our algorithm does not require the matrix to be non-singular. And then we also generalize to a kind of, something called Clifford tensor networks, where you have a set of tensors which need to be contracted, and each tensor, when viewed as a vector, is a stabilizer state. And that, I don't want to get into the details of that here. I don't really have time to define what I even mean by a Clifford tensor network, but one can generalize our algorithms to that setting as well. And so, remember that we were motivated by this question of, do shallow Clifford circuits provide a quantum speedup in terms of gate complexity, or the total number of operations? And what our results show is that maybe it's possible that that's not true on planar graphs, because if omega is 2, then our algorithm has a roughly linear runtime classically. However, another way to view our results is to say, well, it's all consistent with simulation of Clifford circuits being very similar to other linear algebra tasks with the same kind of geometric restrictions. And so I would say that this hidden linear function problem for Clifford simulation on sparse but non-planar graphs, as far as we know, there could be a polynomial speedup, quantum speedup for that task. And that's all I wanted to say, so I'll end there and stop for questions. Thank you.